just maybe to set the scene, because I know some of you are coming and going, and we are working in different time zones here and so on. So there have been a mix of talks, some more technical, some less technical, some more information science focused, some more philosophical, some very technical. So I guess yours will be the most technical and most mathematical of all, without trying to jump ahead to the other three talks, but I guess so. And that's in fine tradition of Google talks we have had in the past at Search Solutions, because they always tended to be highly technical, because obviously we're interested in people who know what they're talking about, and not people who want to sell stuff. So on that note, I'm happy to hand over to you if you want to share the screen.
Yes. This is a talk about TensorFlow ranking, which is a library that my team built over the past, I guess at this point, almost 2 years now, for basically learning to rank at TensorFlow. I'm presenting this, but it's on behalf of my entire TF ranking team. So what is TF ranking? TF ranking is basically a library that was built to provide learning to rank functionality for ranking problems in TensorFlow. Since we found there was a big gap there. There was nothing in TensorFlow that actually allowed people to build ranking solutions very easily. So we open sourced it under TensorFlow ranking on GitHub, initially released on December 2018. And it's still actively developed by the TF ranking team at Google Research. And I'll actually tell you more kind of towards the end of the talk about some of the active developments that are happening right now. It has been widely adopted by the industry. It's, you know, from what we know, and, you know, we don't know all the solutions that were adopted, but from what we know, it was launched in products by companies such as LinkedIn, Grubhub, Jihu, IQIY, and also been, you know, actively experimented by other teams like teams at Uber, Walmart, Spotify, Airbnb, and others. So pretty wide adoption. Also in terms of the publications, we do see a lot of citations for this library and people using it. So pretty happy to see that. To kind of brag a little bit about the library, we have state-of-the-art on a couple of public benchmarks. There is this very popular passage ranking task that a lot of people compete in, MS Marco. On that leaderboard, we actually #1 on passage re-ranking task, which is kind of the main task for which TensorFlow ranking is suited. And then we also know #5 of passage full ranking task in collaboration with some other teams. We also participated in Track COVID, which was run, you know, this year as a response to the, you know, COVID pandemic by Track, by NIST and AI2 and some other companies and institutions in the US. And we achieved really good results, which with this technology we call TFR BERT, or TensorFlow ranking BERT, which I'll talk a bit later about. In rounds 5 and 4, we achieved basically best performance across metrics on this competition. For those of you who don't know what learning to rank is, which I assume most of you do know, but I'll go very briefly about this. Is basically the problem is we have here a function f that takes in unordered inputs, and then it tries to order them in the most kind of the best order of relevance, the optimal order of relevance. And of course, it has application in a bunch of different domains, such as search, question answering, recommendation systems, and others. Okay, so what's the problem here? The problem here is we try to learn a scoring function f to sort a list of examples. The input of the function is a context, a list of examples, and labels. So a context here can be something like a query or a user, if you have a recommendation systems problem. And then the output of this function is basically not a score or a classification score like you would do in normal classification ranking, but a function f that produces the optimal ordering of examples. So, you know, very formally, we have this training samples XY, which is basically the features and the labels. And we try to produce function f here that tries to minimize some empirical loss. And how to choose this empirical loss is actually the core problem of learning to rank. Here is a very, very kind of brief explanation why this choosing the loss function for what I described before is a hard problem. So standard ranking metrics are basically what we call discontinuous or flat everywhere, and cannot be directly optimized with gradient descent because they're not smooth. So here's an example. We have, let's say, two documents, T and S, and that's a delta between their scores. This is kind of on the x-axis we show the difference between their scores, and on the y-axis we show their ranks, right? So rank is basically, or in a rank here I mean just whether they're swapped or not in ranking, the document S and T. So basically the swap itself is a binary operation, so it can be either 0 or 1. So as long as the difference in their scores is below 0, it will be 0, the swap, and if it's above 0, it will become 1. So it's basically, if you want to optimize sort of the ranking of the entire ranked list, it's going to be very, very difficult to do using, or kind of impossible to do in this way using gradient descent. So you have to apply a bunch of tricks here to kind of find approximate inference for this loss function. This is just an example of why this is a hard problem. So how do people approximate these things, right? So there's a couple of approaches. One very simple approach, but still is used widely and still is pretty successful, is something we call pointwise learning to rank, or LTR. So pointwise LTR, some examples include order linear regression, classification, GBRT, and so on. Basically, what we do is we take each document independently. So in this case, we have document F, A, B, and C, and we estimate the probability of each document being relevant. That's pretty much reducing the ranking problem into classification problem. That's pretty much what we do here. Pairwise methods. So pairwise methods take pairs of documents. So we have document A, B, C here. What we will do is we will actually try to compare document A and B, and compare documents B and C in this case. So what you can imagine is sort of a pairwise classification. We take a classification of whether one document is bigger than the other document, that kind of thing. And examples here also include things like RankNet, RankSVM, RankBoost, a couple of pretty well-known learning to rank methods. For listwise methods, we consider the entire ranked list, right? So we take F of A, B, and C, and we try to produce pi star, which is basically the best possible ordering of ABC. That's, I would say, probably state of the art in learning to rank methods. Examples include lambda mart, approximate NCG, and some other methods like listnet or listmle, which I can present shortly. So what we do before I go on, like what we do in TF ranking to sort of connect, what we do in TF ranking is basically we try to implement some of these state-of-the-art methods, or at least some of these losses into sort of a coherent framework in TensorFlow. So one thing to talk about learning to rank is that traditionally it's been sort of this standard approach for machine learning, where you take features that are handcrafted. So you can handcraft them based on query document pairs. You sort of create these features based on TF-IDF scores, URL length, page rank, page quality, and so on. And you create this, handcrafted features. They're numerical. You encode each query document pair using these numerical features, and then you create human relevant judgments for these pairs. And the large data sets that are openly available, like Web30K, Stella, Yao, learning to rank challenge data set, they're all around 30,000 queries. So there is sort of a limit to this approach because you can't manually label millions or billions of examples. Deep learning to rank goes a different direction a little bit. We basically try to now use sparse features, directly use query and document keywords as features, rather than try to numerically encode them using things like BM25. And often they rely on large scale data. So, often we take user interactions as labels versus, the documents themselves, the labels themselves. And so that comes with some price of, the clicks being noisy. And also, again, there is a lot of recent work, which you probably heard about at this conference and other conferences, about things like attention models, BERT, and other, neural architectures that have been very, very powerful in modeling text, images, audio, and so on. So we'd like to incorporate those into our sort of learning to rank method as well. There are a couple of, I think, technical challenges. As you mentioned, there's a couple of technical things I want to discuss. How we actually tackle this learning to rank in TensorFlow. So first of all, I would say sort of the key block of TensorFlow is this TF example, which is data format, but it's not really useful for representing document lists of varying size. And I'll describe why in a second. Also, there is this notion of losses and metrics, where TensorFlow itself has no built-in ranking losses and metrics. And again, this is important for ranking, as I described, because ranking has its own sort of idiosyncrasies when it comes to modeling losses. And also, serving may differ from training. This is a little bit more complex, but the idea here is that when we train a model, we need to see the whole list of documents. So basically, we need to see the whole list of query document pairs. For a given query, we need to see all the documents that it may retrieve. At serving time, we may only see one document at a time, depending on the implementation of the underlying retrieval system. And so that sort of needs to be overcome. I will not talk about this aspect too much in this talk, but it's something that people should think of when they deploy these type of TensorFlow or large-scale models in production. So here's a very brief example of what we call ELWC, example list with context, that comes to combat the first question of how do we represent inputs to these models. So in this case, each query is by itself a TF example, and each document is also a TF example. And what we have is basically a special list of examples where the first example is a context for a query. So it contains the query tokens and basically what they are. And the second, third, fourth, and so on, like all the rest of the examples are the examples themselves, are basically the document associated with the query. And they can contain basically things like, again, document tokens or other features, and also the value, which is, are they relevant or not to our query. So in this way, we can sort of pack lists of different size of different queries, right? So for query 1, in this case, we have 3 documents. For query 2, in this case, we have 2 documents. And they have a query association, but at the same time, they still follow the TF example format. But in this way, we make sure that all the documents for the same query will go to the same worker in TensorFlow, so that when we do sort of the batch processing, when we compute the losses, all the documents will be seen at the same time. That's something that we need to take care of when we do sort of the distributed processing of data in TensorFlow. I talked a little bit about this. So, this is kind of the standard supported components that TensorFlow ranking has. It has losses, metrics, sparse and embedding features, and also something I will not talk too much about this in this talk, but something very important is sort of what we call unbiased learning to rank from biased data. So how do we actually learn from clicks which are biased and noisy? Some examples of supported losses in this framework. We support a lot of sort of the standard pointwise, pairwise, and listwise losses. So the nice thing about this framework is that if you as a developer are not necessarily committed to listwise approaches, but you want to try something simpler like pointwise, you can easily do that. And then later on switch to something maybe more advanced, like the last one here, ListNet, which is at this point probably state of the art in neural ranking losses. Right, so it's very easy for you as a developer to sort of go on the spectrum of pointwise to listwise. In general, TF ranking works like any other sort of TensorFlow library, except for the fact that we have, again, here ELWCs and not examples as inputs. Scoring function is basically neural net, or you can develop your own architecture here. And losses are what basically drives the parameter updates. And again, they can be either pointwise, listwise, or pairwise. Okay, so now I'll spend the rest of my talk talking about some new developments at TF ranking. So far, I've been talking about things that are been available for a while. These things have become available earlier, I would say earlier this year, or maybe like very late last year. So the last 3 things I'm going to talk about are TFR BERT, these advanced scoring functions that are based on transform architectures that have been very powerful. Neural GAMs, which is sort of neural version of generalized additive models for building interpretable and explainable models. And the last one is document interaction networks, which allow for modeling cross-document interactions in your ranked lists. And as I'm speaking right now, 1 and 2 should be fully open sourced, and I think 3 is something we're working on. So you can make use of these things today or in the very near future. So TFR BERT is a very simple adaptation of BERT to listwise ranking. The idea is very simple. As we talked before, what we have here is we input example list with context. The smart thing here is that how do we encode the list using a BERT architecture? So that's what TFR BERT handles. We basically create this query document lists using BERT architecture. We then feed them into the scoring function and then update the model parameters with listwise losses or some other losses. As we're going to show here in the next slide, if we fine-tune the model using what we call softmax loss, so basically listnet style loss, where this is the cross entropy between the basically the softmax of the labels and the softmax of the BERT scores, we do get pretty good results. So here we compare 3 loss functions using this TFR BERT architecture. These are results on the MS Markov passage ranking, which I mentioned in the beginning. So in the final submission, we actually applied some tricks, but basically these are a comparison of just the losses themselves, sigmoid, pairwise, and softmax. When we compare softmax data outperform sigmoid, we do have some tricks about how do we ensemble losses in a smart way. So one way you can do it is you can basically ensemble the outputs of all 3 loss functions. And then, as you can see, you can further improve the results by doing this ensemble. So it means that, if you do have capacity to do more complex models that take into account multiple losses, you can actually do better. But if you, only want to run one model with one loss, probably softmax loss would be the best bet in this case. I'll move on to interpretable learn-to-rank models, which is what we call neural GAMs or neural generalized additive models. For those of you who don't know, generalized additive models are basically these functions that encode features. So what we do have is that the final model is still a sum of parameters like these functions, but this function can be nonlinear. So it's very similar to linear regression, but instead of linear composites, each composite can be like an arbitrary function of any type. So the interesting thing about learning to rank with generalized additive models is this idea that we have context, we have a query. So we need to incorporate the information. So this is an example here. We have hotels and we have user device, which is the context, some sort of modeling of the user. And then you want to output some list of hotels based on some relevant score, right? Then we have relevance, price, and distances, let's say features. And the weight of these features, again, may depend based on the user device. That's the idea, right? So potentially, like, maybe if you're searching on a mobile device, distance should be more important than price, and vice versa on a laptop. When you're ordering well in advance, price is maybe the most important factor, and so on. So with these type of generalized additive models, what we can do is we can basically create a weighted combination of these functions, like additive functions, which is weighted by some context. So to give an example here, in the right-hand side, we have sort of the architecture that drives it. The left part of the tree is individual models for parameters x1, x2, x3. Think of these as like relevance, distance, and price. And on the right-hand side of the tree is Q1, Q2. This is kind of the user or context or query-based features. And they interact together here at the upper level. So in some sense, we create a weighting of individual document features based on the context. And note here that each of these features goes through its own neural network. So in some sense, you can think of these as individual neural networks for each individual feature. So why is this important? So here's an example of why. I think there's been a lot of discussion in the last year or two about like how important for our models is to be interpretable or explainable, so that we don't just have a black box model, but we have something that we can explain to the user. What we see here is that in this type of model, we can actually model using a function each individual component of the model. So this is an example from a Web30K collection. We can not only create a model for each of these different features like LMRI, JM, and how it affects the relevance, but also we have some technique to distill the submodels as what we call piecewise curve. So we can actually see how the model behaves, how the feature behaves in the model, right? So just an example, mean of term frequency, as you can see, it kind of grows and then it sort of stays stable. So the explanation here is basically, yes, you should have some sort of term frequency, but once you reach a certain point, it saturates and stops contributing and so on. So this sort of gives you some sort of explanation of why this feature is important and how it should behave in the model. So this is something that the model gives you directly, not something that we model. It also gives you a nice sort of measure of the context itself. So as you can see here, we're trying to measure the effect of context features. These are the features that we have, and this is the context here. The context is a country. This is on some internal applications that we have. That's why we don't actually spell out the features here. But as you can see, sort of the weights of the features in countries like US and Great Britain, they behave somewhat similarly, but differently from features in the other countries. On the other hand, Australia and New Zealand, again, behave somewhat differently, and again, different from India and Brazil. So this sort of gives you an explanation of how context features can affect your features as well. So this sort of model gives you not only the strength of a neural network, but also some sort of interpretability and explainability. And again, it can be very important for some applications. Here, I just want to show examples of how we perform compared to other standard approaches. We do quite well. We outperform what we call a tree rank GAM, which is some sort of a truncated version of lambda mart that doesn't take very deep trees, but takes very shallow trees. So it sounds somewhat comparable to neural rank GAM in its expressiveness. However, it's hard to model context using these tree rank GAMs because they cannot handle very well sort of the query-based features or the context-based features. And so in applications where you need to take care of the context or query-based features, you can do really well with this neural rank GAM plus, which is the one that includes the context of the user or the query. So do check it out if you're interested in interpretable models. I will finish this talk by again giving this one last example of a new advancement in TensorFlow ranking, something that's called document interaction network, which is basically a very old idea, I think, in information retrieval, but the idea is still sort of relevant today, is the idea that document is not sort of stand on its own. It should be ranked in correlation with other documents in the ranked list, right? So the way we model it here in this framework is we have this document and we have this document set. So the document set is basically the list of all the set of all the other documents in the ranked list. And we create a self-attention layer that combines the document and the entire document set, including document itself, which sort of learns the attention between all the documents in the set and the document here. And then we have another layer, which is the concatenation layer, where we also feed the query. So basically, we have three inputs: this attention layer, the document itself, and the query. So we learn sort of the query and document representations that are relevant to this attention set or attention layer set. In some sense, this is very similar to, I would say, things like relevance feedback in information retrieval, where you try to use the retrieved list of documents to come up with sort of the best representation of the query using the terms that appear in this ranked list, right? So that's sort of, I would say, classical alternative to this sort of more neural network style approach. And again, we do show this works quite well on public data sets. This is the Web30K benchmark. This work appeared in ELTR, I should say. So basically what we show is that compared to both LambdaMart and a bunch of neural network baselines, it performs quite well. This is the last portion here. Overall, it's known that on the kind of traditional benchmark like Vector-AK, YAO Learning to Rank Challenge, Stella, LambdaMart, or in general tree-based methods do tend to outperform neural rank-based methods. We did some strides in this direction in the last year, but you can see here that in this particular case, we actually managed to either outperform or be comparable to LambdaMart, which is the light GPM here, which is pretty remarkable because if you see, like in this quadrant, we have all these newer neural methods, and they all seem to be well below the LambdaMart sort of performance. So it does show that in coding context can go a long way towards sort of improving the neural models to the point where they're competitive to models like LambdaMart on smaller size data collections. I think this sort of draws me to the end of my talk. To recap, TF-Rank is a deep learning library for learning to rank. We try to implement as many as possible common ranking losses and metrics so that people can directly use this out of the box and apply to any applications that they want to build in ranking. It is also, we think, well suited for things like handling sparse text, which is very important, again, for newer applications of ranking that include things like BERT, deep neural networks, things like the deep cross-document interaction that I described before. Again, like using the raw text of document and query did become very popular and is very powerful. So TensorFlow ranking is much more suitable for this than, let's say, things like light GBM implementation of LambdaMart. And it does scale to massive datasets because we basically inherit the scaling from the TensorFlow component of the library. This is standard TensorFlow ranking. I also described sort of a few state-of-the-art solutions for industry applications, including TFR BERT, Neural GAM, and document interaction networks, which again will be coming soon in open source. But the other two you can check out now in our GitHub. Guess time for questions. Again, sorry for being late, and you can try out the demo of TensorFlow ranking here at the git.io /TF ranking demo. Thank you.